Good afternoon, ladies and gentlemen, and welcome to this afternoon's panel titled Graphene for Automotive Applications, Lighter, Stronger, Better, Part 1. Before we begin, I wanted to go over a few logistical items. First, this panel session is scheduled for 45 minutes. Second, we invite the audience to submit questions through the text feature of this webcast, located in the lower part of your screen. We may not get through all your questions, but we will certainly do our best to get through as many as possible. If you're having any technical difficulties, please refer to the help desk on the bottom of each page. For maximum bandwidth capabilities, please place all your local smart devices and other laptops in sleep or airplane mode. This should help with any buffering issues. Now, it is my privilege to introduce to you our panel moderator, Terrence Barkin, Executive Director for the Graphene Council. Under Terrence's leadership, the Graphene Council has become the leading global organization promoting the adoption of graphene-enhanced advanced materials on an industrial scale. Ladies and gentlemen, Terrence Barkin.
Thank you, Frank. Really pleased to be here and working with SAE International on this important session. I won't go through too much detail about this, but the Graphene Council was founded back in 2013, and today we reach more than 27,000 material scientists and engineers with an interest in graphene for advanced materials. We have in our membership a wide range of companies that include academic institutions, as well as graphene producers, intermediaries, and end users. And as you'll see in this slide, Ford Motor Company is one of our valued members on the end user side that is using graphene in production vehicles, and we'll hear a little bit more about that today. So the Graphene Council has been involved in the setting of standards for this material, in the evolution of how it's used in different applications. And to date, we have identified more than 40 major application areas and vertical markets where graphene can be applied, including in composite materials, for example, energy storage devices, coatings, and many other applications that have relevance for the automotive sector. And we can go to the next slide there, Frank. Thank you. Graphene was only discovered or isolated back in 2004, and in 2010, the Nobel Prize in Physics was awarded for that discovery. Since that time, the market has gone through tremendous evolution, but we've arrived now at a point in 2020 where we have mature production capacities, and we have a great understanding of how to use this material to enhance applications to really drive step change improvements. And you're going to hear about that today from two excellent presenters. The Graphene Council is an open, neutral trade association, and we would welcome membership if you have an interest in learning more about graphene. We have in-depth market reports of over 600 pages detailing production methodologies, application areas, market pricing dynamics, and evaluations of more than 200 graphene producing companies. So with that being said, I'm very happy to introduce our two experts on our panel today. The first is Paul Redinger from Chromaflo, which has tremendous experience in the automotive sector with nanotechnology and coatings. And the second presenter you will hear from today is Dr. Phil Rose, the Chief Executive Officer from XG Sciences, based in Lansing, Michigan, and again, with a lot of experience in the automotive sector. We are going to hear from both of the presenters first completely. If you have questions, put them into the attendee question box, and if possible, indicate for whom your question is. And once the two presentations have been made, we'll take a Q&A session. So without any further delay, Paul, it's all yours. Looking forward to hearing from you. Thank you.
Good afternoon. My name is Paul Redinger. I'm with Chromaflo Technologies. We do work with liquid dispersions of graphene for automotive applications, and hence the title. Give you just a little bit of background on who Chromaflo is. We are a global manufacturer of color and specialty chemical dispersions. We have facilities our headquarters is in Ashtabula, Ohio. We have a manufacturing plant in Rockland, Ohio, Brampton, Ontario. We have facilities in Mexico, in Sao Paulo, Brazil, Sittard, Vantaa in Netherlands, also Vantaa is in Finland, Maastricht is in Netherlands. We have facilities in India, South Africa, Shanghai, China. We have a brand new facility in Kuala Lumpur, and we have a plant also in Dandenong, Australia. So we literally have a foothold in every continent and are able to support you in your needs. Now let's talk a little bit about what nanocarbon is. Nanocarbon is a material that is basically derived from basically a number of different ways. But basically, the most simplest way to think about this is when you write with your pencil on a piece of paper, you leave a mark, right? And that mark is actually comprised of millions and millions of layers of carbon, right? And actually, those carbon layers are each comprised of sheets of what we call graphene that comprise ultimately the crystal we know as graphite. And if you take graphene, you graphite and you break it down, you can get a graphene sheet, and the graphene sheet can then be rolled into what we call a carbon nanotube, and the carbon nanotubes can take a variety of forms, including single wall, double wall, triple wall, or multi-wall carbon nanotubes. So all these types of materials are all kind of related, and they have a few things in common. So what specifically is graphene? Well, graphene deals with close-packed hexagonal arrangement of carbon atoms at the atomic layers, and for practical intensive purposes, it's two-dimensional object, although it is technically 1.7 angstroms thick on that scale. So it's basically two-dimensional object. You can do a number of things with a single layer of graphene. If you have it cut to a certain shape and you roll it into a ball, you can get fullerene. You can also roll it into, as I mentioned, carbon nanotubes. And the other thing that can happen is you can unroll it and have platelets. Now, the interesting thing about the platelets is for a lot of time that people did not think the platelets would be stable or able to survive, able to exist on their own. And that was the case until 2004 when Konstantin Novoselov and Andrei Geim at University of Manchester did an experiment with Scotch tape where they took graphite and they began splitting it in different layers, and they kept repeating the splitting of the layers between sandwiching graphite between that Scotch tape until they actually eventually isolated single layer graphene, for which they won the Nobel Prize in 2010. So what are the properties of graphene? As I've kind of mentioned here, here's a picture of the lattice, right? So you have sp2 hybridization orbitals between carbon atoms that's very flexible, very strong, very durable. The surface area of a gram is typically on the order of 2,600 square meters per gram. The aspect ratio will typically vary, but a single layer graphene will transmit up to 97.7% of light through it. It is extremely strong in terms of its gigapascals, 130 gigapascals, something on the order of 18 times stronger than steel. It is also very stiff, and at the same time, it's amazingly flexible. So chemically, it's easily processed, but there are catches to it, and the density can vary somewhat depending upon the specific nature of the material you're dealing with. Some of the material performance characteristics include mechanical reinforcement, color and appearance, electrical conductivity, barrier properties, weight reduction, robustness, thermal conductivity, improving flexibility, ironically, and also as an anti-static, flame retardant, and thermal stabilizer. So just a few of the things that can be done with graphene. Some of the challenges around it is for a long time it was very difficult to produce large volumes of graphene. There's costs in terms of capital equipment necessary for producing graphene. I should mention too, there's differences in very different techniques for manufacturing graphene, and you can divide them to two different basic types. One would be like a top-down, which is where you start with graphite and you split it into the individual layers to eventually, break it down into eventually the single layer graphene. And the other direction is where you do carbon vapor deposition. I'm not going to get a whole lot into that today because that's a very complex topic in of itself. But another challenge that comes out of this then is if you have differences in technique, you have issues with respect to how do you control quality. And there's potential for lot variation in surface area, layer surface depth, changes in surface chemistry, and defects that can dramatically change or affect all the properties that make graphene unique. With respect to final applications, there's also other challenges, including processing, viscosity control. What does it do to your polymer kinetics? Does it change your polymer chemistry? Does it affect your conduct in order to achieve conductivity? Are you able to get a defect-free graphene sheet? Are you able to achieve your improved dispersion or low percolation? For mechanical properties, you need to have load transfer, which basically means you need to have a good dispersion, and you need to have a height interfacial tension. We'll talk about that in a little bit more. Thermal conductivity's got different characteristics it has to achieve, including thermal resistance, and you don't have to actually have particle-to-particle interface, but there has to be a degree of phonon scattering. And we'll talk about, but if I go too fast, have any questions, feel free to ask me questions later. Overcoming barriers, the final properties. One of the several routes that we can take. One is through covalent functionalization. On the very edges of the graphene, it's possible through the presence of the sp2 hybridization to perform a nucleophilic or other type of chemical attack on that area edge there, and then you can bond the chemistries to the substrate. Another approach is to blend it into polymers and compound it in such a way that you're working with polymers that have the affinity for it. One of the things I should mention is that about graphene is that the van der Waals forces and the attraction between platelets tends to be very strong as you approach single layer graphene. So having steric stabilization becomes very important, and that kind of takes me back in the direction of going to pi-pi interactions where you actually have a molecule or a series of molecules that have affinity for the surface, and then a tail that is compatible with the polymer. And then also you all have electrostatic interactions because you can have polar groups attached to it, and then you can have charge stabilization as well. So there's a number of different routes to making a material become compatible with your system. Now I'm going to show you a TEM image. I'm going to explain a little bit more detail what I mean about the difference between graphite and graphene. Over on the left-hand side, you have a picture of graphite, or TEM image of graphite that is literally hundreds of layers thick. And you can see down here, if you look at the edge along to this middle here, you can see layer after layer after layer after layer of atomic layers of graphite. And when you have lots of layers that are done from this, you see basically you can see that that's not a thin layer graphene that you're working with. That's actually graphite. Now a graphene here, this is actually still multi-layer. We would call this few layer graphene. It's actually got like 4 or 5 layers, very small here. You can identify them right on the edge. It's 1, 2, 3, 4 edges of graphene. And the other thing about looking at a TEM micrograph of graphene is you can actually kind of get a look at the hexagonal matrix, which was it's in resonance all the time, and you can kind of get a glimpse of what that actually was taking place there. So talk about this a little bit more now. Back in 2013, Santosh Yadav and others at Konkuk University in Seoul, South Korea, did a study where they tried to study the difference between what we would call functionalized grafting, where they applied polymeric modification to the surface, versus pristine grafting that they didn't, and they compounded it into a urethane composite. And what they found was through SEM microscopy, they found that if they had functionalized the graphene to be appropriate for the material that they're working with, they achieved a very strong interface between the polymer and the surface of the edge of the graphene, which you can kind of make out in this particular SEM micrograph on the left. On the right-hand side, a weak interface shows that you actually have fracturing, which results in a polymer pulling away from the surface of the graphene, and that tends to result in weak properties. Further on, he also shows that depending upon how you do this, you get a very different fracture mode in terms of the material that you produce. If you break the material that has a functionalized graphene and you look at the very edge of it under an SEM micrograph, you still see a smooth edge, and you see the graphene platelets are still immersed in the polymer. Whereas if you're working with an unmodified, untreated graphene in there, there isn't as strong an interface between the graphene and the polymer. And as a result, you get a fracturing where the platelets are broken open and exposed and separated from the polymer. And that's what you see on the right. So there's some examples of some of the things that they found that kind of shapes our thinking today. That has the whole issue of load transfer has a very significant impact upon the types of properties you're going to achieve. And they found that with respect to your braking stress, it can increase your braking stress by as much as 10 or 15%. Improve your braking strain similarly, but then the impact upon modulus in terms of what you were able to accomplish with load transfer improved vastly by like like 1,000% in some cases. So there's a vast difference in terms of what you're able to do versus, it's just a massive amount of difference between what you can do with a graphene that's been properly functionalized for your application and properly dispersed for your application versus one that is not. This also has an implication for the improvement of the thermal stability properties, because you can get a 30-degree increase in thermal stability from the use of these materials. So what does that mean to us today? Well, I have a short list here of some graphene dispersions that are dispersed in some of the polyols. This isn't everything that we have, but this is just a few of them. We have graphene dispersions that are designed for polyol and polyurethane applications. We have graphene dispersions that are designed for plasticizer-based carriers and plasticizer-oriented applications. We have a variety of different dispersions with different characteristics and different properties, depending upon the types of properties you're trying to achieve. And we have compatibility from things like monomers to polymers, plasticizers, waters, solvents, styrene, polyester, epoxies, and polyols. The important thing is it's important to understand that you have to have a compatibility between the material you're dispersing in and the material you're actually using in your final application. And there has to be the whole process from the manufacture of the graphene to up to the point where you actually mold your final part or coating, apply your coating, really makes a difference in terms of what types of properties you achieve. So one of the things we did here was we did a dynamic mechanical analysis study, and we looked at what happens when you take a polyester graphene composite, in this case, and we looked at different loadings to see what impact it has on the modulus. And one of the things we see here is with a dynamic mechanical analyzer, we're able to look through a sinusoidal wave over a range of temperature, and we're able to see the impact that graphene is having at very, very low loadings upon the modulus properties of a polyester composite, and that in turn translates into what that means fairly significantly in terms of your compressive modulus, so in compressive strength. So looking at this here, at 0 point, your control is right here in terms of the modulus you're getting, starting off at about 2.5 gigapascals storage modulus at 25 Celsius, and you can increase that modulus by when you get to 0.1 or 0.5% between 18 and 28% increase in modulus. Now, the impact it has upon a glass transition temperature is not really huge. It only stays within a few degrees. So that tells us that it's not really changing the crosslink density all that much. It's behaving relatively stable. But the interesting thing is, you can get to a point, if you increase your graphene concentration, you can eventually get to a point where it will increase the TG simply as a function of space between the molecules and their ability to move. We'll look at a similar situation with an epoxy and a graphene application. And with epoxy graphene application, we can go to, again, about 0.1% graphene, and that's a very, very low loading of graphene that will allow you to achieve a significant gain of about 18% in terms of your modulus. Again, and then in terms of the crosslink density, we have to be careful too, because graphene can, if it's not dispersed properly, it can affect your crosslink density when you're trying to do a polymerization by steric interference. But in this case, we're finding that the impact is not significant. So one more thing I'm going to mention in here, and that is about the dispersion characteristics will also impact upon your electrical conductivity here. Here in this graph, I'm showing from 0 to 3.5% graphene. I'm showing we're at around 1.5% graphene concentration. Looking at this, and we're looking at two different types of conductivity. One is one-dimensional, point to point, and the other is three-dimensional in terms of volume. And we see that with a properly dispersed graphene dispersion, you can achieve a percolation on the order of 1 to 1.5% when you start to see a significant increase in electrical conductivity in a vinyl ester type composite. Another case, if you do not have it dispersed, it will take you a much higher loading before you achieve a similar type of percolation threshold. In this particular case, we're going up to above 2.5 and 3% before we start to see any type of percolation at all. So the type of characteristics that you have in your system, really in terms of dispersion, is really important, and how you incorporate it is important. Some of the benefits are of using the dispersion are to give you a dust-free dispersion, but really the central issue surrounding this is to have the graphene, the type of graphene you're using, and the type of processing you're using for it, the types of polymer and composite matrix that you're using it. These things all kind of have to fit and work together. And so our thinking in nanotechnology is really to help you understand, or is try to help you be aware that how you handle the material is going to play a role in how the types of properties you're able to achieve. And I thank you for your time, and I will turn the presentation back over to Terrence.
Well, Paul, thank you so much. That's a lot of information in a short period of time, and I appreciate that very much. Without any further delay, we're going to go to Dr. Phil Rose from XG Sciences, and we'll get a little closer look at actual applications of this material with our good grounding of some of the behavior of it. So with that, Phil, let's hear what you have to say. Thank you.
Thank you, Terrence, and also to SAE for the opportunity to participate today. What I hope to be able to do is provide you with some examples of graphene nanoplatelets are being used for commercial production and automotive applications, and at the same time provide enough context in 10 or 15 minutes or so that you might make an extension to their use in applications in your respective areas of interest. I have a few perfunctory slides we need to go through. Slides are not progressing. Just a second. I think I need to go to this one. Oh my goodness, hold on. Okay, just a moment. Can everyone still see this? There we go. A few perfunctory slides we need to go through that WCX asked us to put in. Also, XG Sciences has public reporting requirements. We are not actively traded in any exchange, but because of our public reporting requirements, we do have to indicate forward-looking statements. So throw that up there for you guys just to look at very briefly. But what I'd like to do is start with just a very brief introduction of XG Sciences. We were formed in 2006, actually based on a technology license agreement with Michigan State University. Of course, a lot has happened since then, but today we're perhaps best described as a platform play in advanced materials, where those advanced materials are what we call graphene nanoplatelets. And the platform really refers to our portfolio of products that leverage two manufacturing processes, both located in Lansing, Michigan. One that is based on the chemical exfoliation of graphite, and another based on the mechanical exfoliation of graphite. So it's through our process know-how we can manipulate the thickness, the diameter, and the planarity of graphene nanoplatelets to optimize their performance in various in-use applications. So we supply graphene nanoplatelets in the form of dry powder, or as a wet or solvent-based cake, as slurries, or as more fully integrated products that may be in the form of a master batch in a given thermoplastic, or as fully formulated coatings with binders, surfactants, and solvents. So essentially what we do is we make our customers' products better. We make them better in a few fundamental ways that include electrical conductivity, thermal conductivity, barrier, lubricity, and strength in a composite. So in other words, these 5 factors are the primary reasons customers will adopt the use of graphene nanoplatelets. So let me provide you with a few examples of how our customers are able to exploit these properties in some real-life applications. So in a broad context, graphene and graphene nanoplatelets have the potential to make a big impact on the automotive industry. In this slide, I highlight a range of applications that exploit the performance advantages of graphene nanoplatelets, although there are certainly many, many more. In red are those applications that are in commercial production today. For example, and of course that's with XG Sciences technology, there are probably other applications out there using other people's products as well. But for example, under the hood parts, adhesives, lead acid batteries, and oils, lubes, and greases are all examples of our products are in production today. There are a few other product areas in engineering scale-up, such as transmission wear parts and coatings. And we also have a number of applications under development which we expect you'll hear more about over the next several quarters, and include things like tires and composites. And of course, are any number of areas that are still back in development within XG Sciences and other suppliers serving the industry. So we won't have time to discuss these applications in great detail that I have on this slide for you today, but I will be able to give you a few examples. So let's go ahead and do that. The first example is the use of graphene nanoplatelets and polyurethane foams. We started working with Ford R&D several years ago when they wanted to explore the benefits of graphene nanoplatelets in various systems. After having demonstrated performance improvements in a range of materials, they chose to first move into production based on the benefit seen for use in polyurethane foams. Fast forward to today, and Ford is in production with our graphene nanoplatelets to enhance the performance of under-the-hood molded polyurethane foam parts, and they've published performance improvements that include 20% improvement in compression strength, a 30% improvement in heat deflection temperature, and a 17% improvement in noise and vibration isolation. Ford first introduced our products in non-Class A parts in late 2018 for applications such as stuffers, pump covers, and fuel rail covers. We did this because there wasn't an optical appearance spec, making it slightly easier to get qualified. We then moved into Class A parts in late 2019 and are now in production on all Ford and Lincoln light truck and passenger platforms. Ford's use is an example where they're able to get multiple performance benefits, strength, thermal stability, and NVH from incorporation of graphene nanoplatelets. In fact, we're able to lightweight the part so that the cost to adopt our products is offset by the material savings. So it's a great example, and I believe one of the earliest of a successful commercial adoption of graphene nanoplatelets in the automotive market. Ford is now considering other materials that may benefit from use of our graphene nanoplatelets. Of course, we're also able to extend the performance benefits to other polyurethane foam systems. This slide provides performance data for use in lower density polyurethane foams. The bar chart on the left summarizes the change in flexural strength and modulus, as well as average sound absorption coefficient for samples without graphene nanoplatelets and those incorporating graphene nanoplatelets from 0.15 to 1% by weight. And as you can see, even small amounts of graphene nanoplatelets will improve the performance, and as shown here, from 50 to 60%. So let's switch gears and briefly discuss applications benefiting from the thermal performance of graphene nanoplatelets. I earlier alluded to a commercial application in adhesives, or at least it was shown on our slide. That particular customer didn't want to provide any performance data for this presentation, but I can say that the application is to improve the thermal conductivity in an adhesive used in production by a European auto manufacturer. They experienced failure in the adhesive due to heat, and our customers solved the problem by adding our graphene nanoplatelets to the adhesive, which allowed the heat to be more effectively dissipated so the adhesive no longer failed. On this slide are two other examples exploiting the thermal performance of graphene nanoplatelets, but neither of these are commercially in use today. On the left are data for use of various graphene nanoplatelets at 5 weight percent in ethylene glycol and water-based engine cooling systems. The data show heat transfer coefficients improving 80% for laminar flow and 35% for turbulent flow, translating into from 75 to 95% improvement in thermal conductivity and with a low impact in viscosity. On the right are some data for use of a paper-like product produced from graphene nanoplatelets. In this work, hybrid design systems replaced liquid-filled aluminum fins used to cool electric vehicle lithium-ion battery packs with a solid-state graphene nanoplatelet-based system. When coupled to the external cooling channels, the system demonstrated a 20% improvement in cooling efficiency and uniformity, impacting not only the complexity of the system, but also the overall cost and weight, both of which are significant drivers in the automotive markets. As a last example, I wanted to highlight the potential benefits for graphene nanoplatelets for lubricity. We do have some commercial business in lubrication, where Hella has introduced an engine oil additive incorporating our materials. We also have a few smaller suppliers using our products in greases, and there's a transmission part supplier planning to launch a product next quarter or perhaps in the fourth quarter using our graphene nanoplatelets. There's yet another aftermarket coating supplier planning to launch a product using our graphene nanoplatelets in the fourth quarter. Actually, we have two aftermarket coating suppliers that plan to launch a product using our graphene nanoplates in the fourth quarter. So the data on this slide are really the results of a customer trial using C500, which is one of our graphene nanoplatelets produced using our mechanical exfoliation process. The data are ball on flat test results for a polyalpha olefin-based oil with and without graphene nanoplatelets. You can see that the incorporation of low levels of C500 greatly reduces the friction coefficient and improves the wear performance. So hopefully I've been able to excite your imagination with some examples of how graphene nanoplatelets may be used in automotive applications. But what really differentiates graphene nanoplatelets from other materials and additives is their ability to impart more than one performance attribute to a given system. And this slide provides you with a view of the many attributes of graphene nanoplatelets that may be exploited to improve the performance in automotive and other applications. This is important as you consider how you may leverage this important new material in improving performance in your own products and projects. It's really an exciting time for the graphene market, and I'm pleased to be able to give you just a glimpse into the potential for this new material. So with that, I will stop here and turn it back over to Terrence for a Q&A session.
Excellent. Thank you, Phil. Really appreciate that. Well, I hope through these two presentations, we've gained an understanding of what graphene is. And first of all, we see that it actually takes many different forms, and there's many different formulations. So that allows us to tune the material to a particular application. And Phil, in particular, I think through your presentation, you were able to show that graphene can enhance many, many different systems and improve many different existing materials, which I think for the engineering community should give us good ideas and as you said, excite their imagination about how to design or engineer parts in a unique way that perhaps they couldn't do before, or to drive improvement out of existing improvement systems. We do have a question from the audience, and this one would be for you, Paul, and it was on your slide number 19. Not that we have to go back to that slide, but the slide 19 was the storage modulus of polyester and graphene composites. And the question was, on there was a graph with a temperature curve, and it showed as the temperatures reached above 100 degrees centigrade, that pretty much all the values were the same. And the question is, why do you think that is the case? Why are all the values the same at higher temperatures?
Terrence, that's an outstanding question. If I may, I would actually like to go back to that slide and make a couple points about that.
Okay, and while you're doing that, Phil, I just want to cue you up to be prepared. If you could show your last slide when we take the next question. There was just a question about some of the range of applications. So just be ready for that once Paul has answered this question. Go ahead, Paul.
Okay. So what we see, generally speaking, is as we increase temperature, we see a loss in storage modulus as temperature goes up, right? And more specifically, this is why it's part of the reason I show the glass transition temperature. When we go above a glass transition temperature, we are no longer really measuring a storage modulus per se, but rather the storage modulus becomes a reflection of the complex viscosity of a material in its amorphous glass-like state. Okay, so we're dealing with a material that has a certain degree of flowability above the glass transition temperature, and basically, in effect, what we're seeing is seeing as a function of these things coming together. It's telling us that these different levels of particles are not impacting upon the complex viscosity of the material as significantly as they do upon the storage modulus below the glass transition temperature. Now, that said, if we were to put this on logarithmic scale, we would actually see some differences. And what we would see is that the higher the loading you go, the higher your complex viscosity becomes.
Excellent. Thank you, Paul. Appreciate you explaining that. So Phil, if you don't mind, if you could go ahead and share your screen with the last slide that you showed, which was the range of applications and functionalities that graphene offers.
Sure. Really, this slide is intended to indicate the range of really performance benefits one could achieve using graphene nanoplatelets. So, the applications themselves are basically endless. We have certain coating customers that will leverage the barrier properties, but also the thermal management properties, where if you put graphene nanoplatelets into a primer coating, for example, you can get the heat to normalize and spread out over the surface of the coating, get very good coating uniformity to improve optical appearance, for example. You can also perhaps get electrostatic dissipation performance if you had an application where you wanted to replace, I don't know, nickel in a on the inside lining of a gas filler tube, for example. So it's really being able to leverage the multiple performance attributes that really begins to excite the imagination. And, in the specific example of Ford, their primary target was really in the strength improvement and thermal stability, which they achieved. The sound and vibration isolation was really an added benefit, which really put it over the top in terms of their desire to adopt it quickly commercially. So this slide was really intended to provide that view more than specific applications, because the applications themselves are actually quite diverse.
Absolutely. Well, having looked at graphene over the last 15 years, the question isn't where can graphene be applied. It's almost where can graphene not be applied. It does boggle the mind a bit, I have to say, that this one material can impart so many different positive attributes to materials. You mentioned briefly, it's not part of the presentation, just again, we're on a time limitation, but you mentioned something with tires. And for forever with rubber and with these kind of elastomers, if you wanted improved traction, you had to accept a higher level of wear, and if you wanted to reduce the amount of wear, you had to accept a lower amount of traction. And graphene has broken that cycle, which is a bit of magic, really, where you can get better wear and better traction at the same time with a small addition. Can you speak just a little bit, because I know there's a common concern about adding graphene as a high-cost additive, and in both of your presentations, we were talking about load factors of less than 1% in many cases and giving these really big performance improvements. Can you talk a little bit about the dichotomy of that? Sometimes when you're actually getting a better performance result when you're using less, not more of this material, and can you also talk a little about the economics of using what ostensibly is a high-priced material on a cost per weight basis, but when we're looking at these load factors and then the percent of improvement, it comes out quite favorable on a cost benefit or a cost to performance basis. So there's a couple of questions in there, and Phil, why don't you start, and then Paul will get your take on those questions.
Sure, thanks, Terrence. Well, you kind of answered the question yourself. It's really, there's a cost performance for any material, for any application, and any given cost, may be warranted in some applications, but in others not so much. We know that automotive is a very cost-sensitive application in general, market in general. So they're always looking at how they can save costs. And the way that you can typically save costs through the adoption of graphene nanoplatelets is either just sometimes through the use of less materials, so you can lightweight things. You can also get a higher performance so that it's more durable, so that the lifetime is longer. But typically adding graphene nanoplatelets, unless you're taking other materials out, do add an incremental cost. But because they're used at such a low weight percent, typically anywhere from 0.1 to really probably the upper limit for most applications is going to be 3 or 5 weight percent. They typically are relatively cost effective in that regard. So there certainly are going to be some applications that just can't accept any additional cost, which means they're not going to pay for any performance. But because you have a wide range of materials available, even within the graphene world, single layer, few layer, large diameter, small diameter, multi-layer, that you can really engineer the materials to perform in many, many different ways, and sometimes ways which you weren't even contemplating. So we have found that cost is typically not a big deterrent for adoption. It's more about ease of use, and Paul certainly touched on that with respect to getting a good dispersion of the materials. And with a good dispersion, you can use lower amounts and get a higher performance level. So there are a lot of variables you can play with that allow you to adopt these materials and get very good efficacy.
Excellent. And maybe, Paul, you could talk to that point as well that Phil just mentioned. And you and I have talked before about dispersion and also engineering for the particular application.
Yes. I think the first thing you want to do when you're talking about costs, first of all, I agree with Phil completely. You want to optimize the amount of material you're using for, and part of that's process for the types of properties you're trying to achieve. And part of doing that is also recognizing that there are going to be different percolation thresholds for different types of properties. The quantity of graphene needed to achieve the improvement in thermal conductivity you need is going to be different from the amount that you need to achieve electrical conductivity, as an example. And I also demonstrated that you get a different potential threshold for improvement to mechanical properties than you do for electrical conductivity as well. So first of all, understanding that. And another thing I think I'm going to mention here, I really think is very possible for graphene to pay for itself in almost any application, because one of the options you do have with graphene is to improve is certainly to improve your modulus and thereby allow yourself to use a thinner part and use less material. So I think graphene, especially when you consider the loadings usages, but the process by which you get there is very important.
Excellent. Thank you for that.
Does that answer the question?
I think so. Yeah, I think it absolutely does. And this is it's really important for those who are on this call and thinking about using graphene and such, is to be able to find partners like the two that we have here today to work with you to work with you on developing the right approach for your particular application, because it's not a commoditized material. It's highly tunable, and the benefits of getting it suited for your application are quite high. We have a couple more questions if we have just a few minutes here left on our session today. One question was related to the use of graphene applications in power, and what I'll suggest is we have another session tomorrow morning, and one of the presenters will speak specifically to graphene's use in energy storage devices, both batteries and supercapacitors. So if that's okay, I'd suggest that you go there. And also, by the way, before we sign off today, if anybody does have any questions about graphene whatsoever, the whole purpose of the Graphene Council is to be a resource for you for information on applications and sourcing for this material. We do have another question, and it's appropriate for our time with COVID-19 and infection control and such. And there's been a lot published about the use of graphene as either an antibacterial or even potentially different forms of graphene mitigating reducing the viral effect. Do either of you want to talk about using graphene as an antibacterial or an antimicrobial material for surfaces in particular?
I can comment on that briefly if you want. One of the properties about graphene is that it's very hard for most substances and most materials to bond to. And so it actually inhibits certain types of bondings and certain types of interactions from occurring. For example, just as a very broad example, is if you use it in a coating to apply to an aquatic marine application, graphene on the surface will effectively prevent many microbial materials from bonding to the surface of the coating. And the same thing can occur at a microscopic level, wherein if you have a virus or a bacteria, and this is a topic that's undergoing ongoing research. So don't try this at home by any means, but there is the possibility that graphene can interfere with the actual mechanisms of the chemical mechanisms by which viruses and bacteria promulgate.
And Phil, do you have a comment on that?
Well, we don't have any experience with antiviral, so I can't really comment on that. We have a number of customers who have used our materials in the formation of fibers, and then those fibers have made it a fabric, and they have reported antibacterial properties for both the fiber and the fabric. So we have seen customers demonstrate that, and hopefully they'll be targeting commercialization of those in the not too distant future. But antiviral, we don't have any data.
Yeah. So thank you for that. There is data, as you say, about antimicrobial or antibacterial, and then antiviral is under study at the moment. So I think with that, we can close this session. I want to say thank you on behalf of Graphene Council. Sorry, we're getting quite a bit of interference. Frank, can you mute yourself for a second? Sorry, we're just getting a little bit of feedback. I just want to close the session by saying thank you to SAE International for allowing us to present. I hope for those of you who are watching, if you haven't been familiar with graphene, that it will have piqued your interest. If you have familiarity with graphene, I hope it shows that it's matured quite a bit and that it's ready for prime time and commercial applications in many, many ways, especially within automotives with their complex systems. And both Paul and Phil, I want to thank you for your time, your expertise, and your sharing of information today. And Frank, I'm going to mute myself if you have any closing comments as we end this session.
Yes, thank you, Terrence. I want to thank you, Terrence, Paul, and Phil for the great discussion today. And a very special thanks to the Graphene Council for organizing today's panel. This concludes our panel discussion and the live sessions for today. Part 2 of this panel session will begin promptly at 8 a.m. Eastern U.S. tomorrow. Thank you again for your attendance. Please make sure to check out the virtual exhibit hall and the on-demand technical sessions, which feature more than 300 pre-recorded presentations from the WCS technical program. Of those 300, more than 70 are focused on design, manufacturing, materials, and lightweighting technology. Thank you again for attending the WCX Digital Summit. Our live program resumes tomorrow at 8 a.m. Eastern U.S. time. Thank you.